My name is Alan Rose from Corrdesa, and today I'm going to talk to you here at Aramat 2022 about how you can support your corrosion prevention control plan with compliant computational corrosion analysis. Another title could be Computational Corrosion Simulation, a new discipline, because I really believe more and more computational analyses will be done of corrosion as time progresses, just like we have thermal analysis, stress analysis, aerodynamics, and so on. So today, what I'm going to talk about is I'll just introduce Corrdesa, and then I'll describe the workflow that we've developed for computational corrosion analysis. I'll refer to some military standards. We do a lot of work supporting aerospace and defense, particularly military, and these are standards that are easily accessible, and how we can use software to comply with these standards towards a better design or material choice in sustainment. So I'll be introducing some elements to this. One of them is our software, Galvanic corrosion prediction software called Corrosion Gin. You could think of this as a 1D approach. And then we'll increase complexity, and I'll introduce a 3D templated approach. The idea is it's the power of full 3D, but there's certain families of geometries that we've managed to categorize and create templates. So an M&P engineer can do a full 3D corrosion analysis but not have that deep expertise of computational simulation. And then sometimes you just have to get right into the nitty-gritty of quite complex assemblies, full CAD assemblies, and as expert practitioners, there's a workflow there where that can be imported and the analysis done. So it's a small company, and interesting fact, small companies in America are defined as companies with less than 500 people, and I think less than 50 million turnover. So we're not just small, I would say we're quite tiny, but we're specialized. We're based in a place called Tyrone, Georgia, which is southwest of Atlanta Airport by about 20-25 minutes. Okay, so I may refer to some of my colleagues. I'll provide PDFs of this presentation if folks like that. So my background, Alan Rose, is computational fluid dynamics and leveraging computer simulation. I've been involved in a number of different physical processes. More recently, the last 10 years or so, electrochemical simulation. Combining that knowledge with my colleague Keith Legg, he is a knowledge expert in coatings replacement, hazardous materials replacement. He works on various corrosion panel advisory boards for Lockheed F-35, for example. And then Siva, our senior scientist, who's developed protocols for capturing polarization data on materials for more accurate galvanic corrosion prediction. So our mission as a company, it's maybe a bit of a mouthful, but I think it describes the 0 to 100 of what we do. So we help our clients quickly develop, qualify, and implement corrosion-resistant materials and coatings, and also their associated application processes and the hardware that does that. And all this has got to be done in a way that meets regulatory requirements, such as REACH. You can have the best technical solution, like cadmium, but you can't use it because it's been banned. And it's not just an issue of, hey, we've got corrosion simulation software, oh, I predict you have a corrosion issue. We need more than that. So what do? I need to either choose appropriate materials or coatings or protection systems or do a redesign. So we're involved in developing software that helps you do that. We've also invented, we've been quite innovative in creating coatings and processes and the hardware that can apply those in an undrip and safe fashion. So our business is mainly software development for material selection. That's our key. We want to provide information to the designers where and when that information is required to eliminate issues that are kind of locked into the design. We also have another leg to the three-legged stool here, and that is the hardware development and manufacture. We've developed a non-drip zinc nickel plating process for repair of F-35 landing gear systems, and that we've sold 50 of those units to F-35. So we've taken development right through to commercial deployment and sale. And then there are services. We keep our expertise sharp. We use our electrochemical simulation capability and engineering capability to guide our clients. So we provide consultancy, and we work on some projects such as corrosion panel advisory boards and corrosion assessment, material acquisition, and so on. Okay, so I'm going to talk about the corrosion analysis workflow. So this is it in its entirety, and I'm going to kind of dig deep into some of these elements. So we are actually software. Corrdesa are software and technology partners with the Siemens organization, and we've incorporated these elements and built them in a workflow in the environment of the SimCenter, the Teamcenter software. So what we have, Teamcenter is actually a product lifecycle management software from Siemens, and it's very widely selling globally. We've incorporated material databases in there, and also for a particular project with the Air Force, we're looking at impact of weather and mission profiles as well. So we have our first look at an issue where we look at the interfaces. We use Corrosion Gin for that. I'll give you a quick demo of that in a moment. There we can figure out how serious the problem is, start making our, planning our approach. Maybe just swapping out some materials or changing coatings that you can do within Corrosion Gin very quickly. Maybe doing that, we can eliminate the issue, and that's it. We move on. Maybe it's a issue to do with design and the actual shape. Anode cathode area ratios are important and have an impact for this particular problem. Looking at like replacement of stainless steel bushings in aluminum structures. So we have a templated approach, and I'll introduce that in a bit. Or we can go full deep dive computational analysis and calculate the corrosion rate map on complex geometries such as that up in the right side there. Okay, let's take a step back. I mentioned earlier on that I will be talking about the military standards. So for corrosion prevention and control planning, it's necessary to comply with a number of standards, certainly in the DoD acquisition. So there's a couple that I will raise to your attention at the moment. We have the MIL standard 1568D, and that's for it's a design criteria standard for materials and processes for corrosion prevention and control in aerospace weapon systems. Then we also have the MIL standard 889. Now it says 889C here, but it's been replaced by 889D, as in Delta, just last July. So the MIL standard 1568D, I think of it as a kind of a bit of an umbrella standard in the sense that there are sections here that I point out. 4.4.1, it says modeling and validation testing shall be performed to identify corrosion-prone locations. So this is shall be language. You have to do this. 4.4.1 goes on to say testing shall include selected materials, assemblies, techniques, and corrosion prevention schemes in relevant environments and in-service loadings. So what I take away from this is before you can do any testing, you need to know what sub-assemblies or assemblies to build for your physical tests. And that's done through computational modeling. And I'm going to show how we use computational modeling to highlight these corrosion-prone locations and guide the design of our test systems. Another thing here we have is galvanically dissimilar materials. It calls out MIL standard 889. So it's actually D. Like I say, it's been released in 2021. So over here on the right hand side, what do we now know about the new mill standard 889D? I'll go into some details, but essentially the methodology is completely changed. No galvanic tables anymore. They actually use polarization data of the dissimilar materials, the conductive dissimilar materials, in order to determine the galvanic compatibility. So this is a new methodology which is based on mixed potential theory, and you calculate the galvanic current, and I'll show you how that's done. So why did they change it? So there was a number of presentations by Victor Rodriguez Santiago from Navarre, and in one of them, I can make them available if you want to contact me. They pointed out the fact that with this very old data, it's not that old data is bad data, it's just simply old. We have a galvanic table here, and as we move in potential to the left, more negative, then we become more active. So these materials up here, graphite, platinum, very noble on the right, moving over to the left to your aluminum alloys and zinc and so on. And titanium is up here near the right, stainless steel is a little bit more to the left, and the aluminums are further to the left. So when they look at the potential difference between titanium and aluminum, it's much larger than potential difference between stainless steel and aluminum. So the standard would suggest that titanium is not a good choice. But this is actually flipped in reality. Over here, we have salt concentration in water, and we have a measured galvanic current of stainless steel, aluminum, and titanium, aluminum couples, materials that were joined together. And you can see that the corrosion current, which is proportional to the corrosion rate, is much higher for the stainless steel aluminum couple. So, clearly the reality there is not reflected with the standard, so that's not really acceptable. So they proposed a number of years ago to change the basis for calculating and determining this compatibility, and to do that they figure out a way to calculate the corrosion current by using the polarization data, which is much more informative. The reality here, I have some stainless steel and titanium fasteners in an aluminum plate, and you can see quite clearly that the stainless steel fasteners create more corrosion on the aluminum plate compared to titanium. So the new standard 889D will also follow this reality. And we can also model this in 3D once we have access to these polarization curves, and I'll show you later. But here's a model where we can see that this higher green activity here dictates the higher corrosion rate around the stainless steel fasteners compared to the titanium. Okay, so let's drill down 889D. The first thing I notice is the title change from Dissimilar Metals. It's no longer called that. It's actually now called Galvanic Compatibility of Electrically Conductive Materials. So straight away, that has a big impact. It instantly impacts a much wider community and many more materials and new materials. We're now talking about not just the basic metals, but also the alloys and other materials that you may choose. Composites, conductive gaskets, sealants, gap fillers, and various treatments all become important and relevant as far as this standard is concerned. Even in the foreword to the standard, straight away they tell you that previously we used galvanic potential difference, and in revision D, the corrosion rate of the anodic member of the galvanic couple is actually used to determine the galvanic compatibility using the mixed potential theory. So they actually have to calculate the galvanic current, or you as designers or M&P engineers have to figure out how to calculate this galvanic current, because that's the method that's now required. And it's done by finding the crossing points of the respective polarization curves. So now there's much more of a demand to get more data, the polarization curves. How do we get the polarization curves? There is an appendix that goes into some detail on it. There are some nuances. It's something that we've been involved in for many years at Corrdesa. We have expertise and lab and equipment to do this, and this is in fact what we do for a number of our clients. So there's a protocol on how to acquire the polarization data. It has to be post-processed and deconvoluted. There's a way of doing that. That gets a little complex, but we have capabilities and tools to do that here at Corrdesa. And then you can go across the curves and find those corrosion rates. I like this approach because I refer to it as a living standard. It's okay, Mill Standard 889D, oh, it doesn't have my materials in it. Now there's a way of going getting that data so that you can use it in your corrosion prevention control planning when you submit your designs and proposals to your DoD clients. Okay, the corrosion analysis workflow. Let's get back to that. How does this all fit in? Well, first, like I said, we have the 1D analysis, corrosion gin. So I'll provide you with a little bit of background on that. Corrosion gin, the Corrdesa software Corrosion gin, is available in the cloud. It's software as a service, so you get access to credentials. It's also available as a standalone and installation on your own systems or a private cloud instance. Just give me a call or email me with any questions. So, how does it work? It's very easy to use. This is just a very quick demo. So what we have here, we choose our environment, and then we describe materials here as substrate, designation, coating, and treatment. By substrate, I mean like the metal, the alloy. Designation could be the type, the series, and whether it's coated or treated as anodized. So we're looking at stainless steel issues, let's say 15.5 pH, and we just click save, and that's basically go, and it gets the data. And we have our group 1 here, where we show the anodic and the cathodic member. That's calculated. And here's the galvanic corrosion rate and the military 889D rating. They put it in categories. So I can create a second group, pre-populated, but swap out stainless steel for titanium, Ti64, like we were talking earlier on. Click save, and it pulls the corrosion curves. And here we have our titanium is cathodic, and now we've reduced the corrosion rate significantly from that choice there. So very quick, we can build up these couples. In fact, one way of protecting the aluminum might be to choose a coating. So we set substrate to any, or coating only, and we pick our coating there, zinc nickel, low hydrogen embrittlement. And now you can see that the zinc nickel is anodic and the aluminum is cathodically protected. So the corrosion rate refers to the zinc nickel. Aluminum is untouched. So, you can look at the impact of coatings. Okay, so that was very quick. And basically what I did was I pulled up 3 groups of pairs. We had the aluminum, 7050. I checked it with 15.5 pH fasteners, for example, or bushing, whatever the fixture system might be. And I checked it with titanium. And then when I went with the titanium, it moved from 271 microns a year of corrosion, galvanic corrosion, only to about 3. And then I switched it and I looked at zinc nickel, and now the zinc nickel was anodic, the aluminum was protected cathodically, and so here's the zinc nickel corroding. So you can do this using the Mill Standard 889D. It's a little bit more cumbersome, but the data's there. There's a limit time which you can fit in a physical hard copy data, a PDF file. But the way they do it here is like the old-fashioned mileage charts, where you choose your materials that you're interested in here, the aluminum, the Ti64, and the pH 15.5. So these are them, 16, 23, and 31. Remember those numbers. So we look from left to right over here for the 7050, and then drop down for material 23 and 31. The intersection is the corrosion rates that we looked at earlier on in the summary table. So that's how you do it. Now all these numbers are various categories of corrosion rate. You have over here your legend. Do note is not consistent. It goes 0.01 to 0.09, 0.1 to 0.9 here. It goes 1 to 5. And it's in mils per year. So Corrosion Gym makes all those conversions. It says it's much easier and faster to use, and it has the same mil standard data. As I was saying, all those numbers are positive. So which one is anodic, which one is cathodic? You have to go back to another table. You shouldn't use this for compatibility, but it does tell you which are more active and which are more noble. So we're going more noble as we go down the pages, the columns. Okay, so maybe it's a situation where it's a little bit more complex, and we have our templated 3D analysis. We use the Siemens Star CCM Plus software. It's a 3D multiphysics simulation software used for many different processes. We use it for our electrochemical simulations. So here we are now. We have a number of a taxonomy of geometries or canonical geometries, families of geometries essentially. A materials and process engineer can very quickly look at the situation and try and reduce it to a simpler element. And what we do here, we have GUIs where the materials process engineer can just put in the key dimensions of this bushing, for instance, and the templates will automatically mesh and solve and report the corrosion rate map. It's very easy. So it puts that 3D power of simulation into the hands of the materials and process engineers as and where the information is needed. Or if it is really complex and it doesn't quite fall into the categories of templates that we have, which are being improved on and increased in number, we can go for the full 3D and we just import the geometry. So an example here is we did some work on FA-18 for the Navy. It was a leading edge flap actuation system, very complex, lots of pieces, lots of area ratios and complex geometry, different materials in close proximity. How can you calculate or assume which is anodic or cathodic a priori? So the workflow itself is just like any other analysis workflow. Whether it's thermal or stress, it's the same kind of elements are in the workflow. You define your problem, you get your geometry. So if it's an old geometry, you still have to prepare a 3D, a digital or electronic file version of it. You can reverse engineer, 3D scan it, or you can just get some drawings and build the 3D. So here's a lug, for instance, where we have a stainless steel bushing, we have the aluminum lug. So essentially by clicking on these surfaces in the 3D model, we are pulling the relevant electrochemical data. And that's what we had, that's what we license, is our electrochemical database to enable these 3D models. And there's an impact that you can, of electrolyte thickness, that you can account for when you're doing the 3D model. So now that you're calculating for the potential distribution, the current density distribution, and on the boundaries of your model you have these polarization curves that define the boundary conditions, you can model a bulk electrolyte situation, a thick layer of electrolyte or something in the ocean or in a lake, compared to the condensate that you might have that just might, a thin layer electrolyte. And there's a difference, because if you understand polarization curves, and we have current density horizontal, potential is vertical, then in a thin electrolyte layer we have more oxygen diffusion, which gives you more aggressive kinetics. So the actual chemistry changes because of that thin layer and more oxygen. So essentially the intersection point here is at a higher current density. So you get that perfect storm of electrical conductivity because you've still got a presence of electrolyte, but it's thin with high oxygen diffusion, giving you a high corrosion rate. And this can be accounted for when you do the 3D models and you have this polarization data. So in a bulk situation, you have more of a spread out corrosion that's quite low, but in a thin layer, you get this intense galvanic corrosion right around the interface of the bushing and the aluminum lug. So, putting all this together, what we have is our corrosion toolbox. Now, we're developing this particular toolbox for the United States Air Force. So we have, as usual, our central Corrdesa electrochemical database. This feeds the 1D, 3D template or 3D corrosion simulation. We also have another database with our Air Force work where we can, it tweaks these deterministic corrosion rates according to the superimposed environments during the mission of the various planes. So, having this database, we can bring in our 3D design, and designers can very quickly do a 1568D compliant calculation. What I mean by that is that the corrosion gin is effectively, rather than manual, where I showed you where I just did click, 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 and I did like 2 or 3 material couples, just at the press of a button, corrosion gin runs for every interface, fastener, nut, bolt within here. It's a computer, so it does it quick. And the result are corrosion-prone locations. So now you have a upfront idea of where you're going to have some issues. Now maybe the material choices aren't appropriate, or as you can imagine with these large systems, you can have tens and hundreds of designers working on the same systems, and maybe somebody just simply either forgot or just made an error. And this would find that. This would show, oh, this doesn't have a coating, or it would spot these high corrosion prone locations. So you can immediately do some changes to eliminate that. And rather than find out later, this is on a C-17, that you have corrosion issues over these fuel ports, once you're out in the field and it's built, this situation can be spotted early in design. But even now, we can still run these kind of calculations, because as we do sustainment, materials change. As I've mentioned before, you can't use cadmium. You may have to replace it with zinc nickel. What is the impact of the new coating on my system when I coat these with zinc nickel and send them out again? So you can use this in design or sustainment. Now, there's 2 paths. Like I said, the materials and process engineers have tools or an approach in our toolbox where they'll say, okay, I'll choose a template that looks like a piece of this geometry here, and they can get their corrosion simulation. Or if you have, CAD experts on board, they can just get the actual CAD of the component, do the analysis, and this is even simplified as well within Teamcenter. Pulls the same data, electrochemical, the materials are the same, and provides the corrosion prediction. Okay, so here are my conclusions. I introduced MIL Standard 1568D, which requires that you identify corrosion-prone locations. I also talked about MIL Standard 889D, which now demands a new methodology for quantifying galvanic corrosion risk, essentially requiring polarization curves, and the intersection of these defines the interfacial galvanic corrosion. Now, there are protocols available for measuring these polarization curves. This is something that Corrdesa do all the time, so we can do that for you, or even help you with that. And then I also presented a workflow of analysis tools, a hierarchy of tools with increasing complexity. There's a push-button CAD operator approach where they can analyze the whole system, which is where corrosion gin is essentially automatically run for each and every interface. Then there's the materials and process engineers approach, where there's families of geometries that are defined with a graphical user interface and 3D corrosion simulation models very quickly prepared without actually needing to know the details of that simulation setup. You don't have to be experts in computational corrosion analysis. It uses a GUI, graphic user interface. And then if it's a very complex geometry and you have those skills, you just suck in the CAD and you can create the full corrosion model of the 3D assembly. And using star CCM Plus, you can get that corrosion rate map. Okay, any questions? You can contact me by phone or reach out to me with an email. Thank you very much.